So we are going to get started. Thank you so much. So thanks everyone for joining us both online and in person. Today we're going to be talking about Python, graphs, and graph neural networks with KNIME. So my name is Victor Palacios and my
Jinwei Sun.
Thank you so much. Okay. So I received my master's degree from the University of San Francisco in data science, and I currently work in the same field at KNIME. I also teach courses, of course, on data science, machine learning, and KNIME. And my initial projects and interests were in the deception detection space and also in healthcare. But originally, I came from a translation background, and so I really fell in love with NLP.
Hi, my name is Jinwei Sun, and I'm currently a master student in data science of University of San Francisco as well. And I work as a data science intern with KNIME, with Victor's. And before this, I hold a bachelor's degree in business, and my concentration was information system. So I dived into the business as my first job. I slowly found the data as actually my interest. So I'm pursuing these careers right now.
Thank you.
Thanks.
Okay. So for today's outline, we are going to give an introduction to what KNIME does, how it works with graphs, then deal a little bit with deep learning and graph neural networks. Afterwards, we're going to look at toy dataset examples and benchmark dataset examples within KNIME. And finally, we're going to talk about building Python-based tools for graph neural networks within KNIME. But first, a little bit about the KNIME Analytics Platform. What is it, right? It is first a data collection tool, which means I can gather data from different sources, but also it's a data visualization tool, which means I can look at many different kinds of visualizations, and I can also do statistical analysis. As well, I can also do data preprocessing. So I can clean my data, check my data quality. And of course, if I can do all of that, then obviously I can do machine learning as well, where I model and evaluate. And finally, I can deploy this to users so that I can have other people using whatever that is that I make. So I can put models into production, all using the KNIME Analytics Platform, which is a free open source tool. Now, how does KNIME work? Well, we drag and drop nodes. So for instance, I can go ahead and grab a table creator node. I can give it a URL. And then for the RSS feed reader node, I can actually then have that access the URL and get some news for me. Then I can do some pre-processing. I can calculate term co-occurrence. And then I can visualize that data in, for example, a tag cloud, as some people may know it, a word cloud, or for instance, a network viewer. And so everything works by modulating. And so if you come from Python, you might think of each of these nodes as a kind of special function. And that's really how KNIME works, drag and drop data science. Now, I'm going to first give an introduction to graphs, and then Jinwei will do an introduction to deep learning, and of course, graph neural networks. So first, what is a graph? It's a collection of nodes and a collection of edges, which of course connect these nodes. You might know this as G is equal to V, comma E, where V stands for vertices. In this case, we're going to use N because it's a little bit simpler to understand. So the nodes here are these circles, and they are connected to each other by the edges, the lines. And each of these real-life examples here can be taken as a graph structure. For instance, in a map, I might have San Francisco and other areas, and each of those constitute a node, and the streets between them are going to be our edges. In a social network, each person might be a node, and the connections between people, for instance, friends or followers, right? That could be an edge. And of course, in chemistry, we might see molecules, and these naturally lend themselves to the graph structure. And there are many kinds of graphs. For instance, there are homogeneous graphs and heterogeneous graphs. Now, a typical graph will have a single kind of node, for instance, people, and the connections between them. But a bar-partyte graph might have people and then videos that they watched. So we can see here, this person here might have watched these two videos, and then this person down here might only share one video with them. And so this could be a good opportunity for some recommendations. In a knowledge graph, we actually have more types. So for instance, it could be a person, a video they watched, and the genre that they frequently watch, for instance. Now for simplicity, we're going to stick to the most typical graphs, which typically have one kind of node. Now, nodes may also have features associated with them. As well, edges can have the same thing. They can have features, but on top of that, they can have weights and they can have directionality. And these are graph properties. So for instance, let's say this is a person. They have attributes like age, hobby, salary. And of course, this other person also has an attribute, but may not have all the same attributes. This is typical when dealing with real data. Then over here, we notice the edges, and they can also have that same kind of features. So this might be a relationship, such as person A and person B are friends, and they became friends on March 24th. We can also have weights. So you see here the thickness of this edge is much thicker than the other edges, which indicates that that friendship, for instance, or that following is stronger. So maybe those two people message each other more often. And so that is one way that we can visualize that weight. We can also have arrows pointing to and from, which is to say following, for instance, this node follows this node, which could be people in this sense, but the opposite is not true. So that's a lot to take in. And of course, for simplicity, we're going to restrict our conversations to nodes and their features. And we're going to let edges simply be edges. They're not going to have features, weight, or directionality. Okay, next, Jinwei is going to present on deep learning and graph neural networks, and a little bit more than that. And then I'll come back at the end. Go ahead, Jinwei.
Thank you very much, Victor. The video so has more interaction with other people. Okay, now let's dive into deep learning. First, we want to know what is deep learning as its terminology, right? Deep learning is actually a really small subset in the machine learning industry. First, we have artificial intelligence, which means that anything that can perform human intelligent tasks. Sometimes right now we have a different way to interpret this AI, which consider like a really smart machines. We think of AI, which is a different terminology we define it here. Well, in machine learning, it's any machine that can learn and from patterns and improve over time that can does human task. And then we have neural network, which is a really small subset of machine learning. This is one algorithm that is trained artificial neural to learn complex pattern, just like human brains. While deep learning, then it only refers to how many hidden layers it has in neural network. If it's a lot of hidden layers, then we consider this as a deep learning process. How does deep learning actually work? First, we have input layers and we have multiple hidden layers. And then in the end, we have output layers to produce the prediction that we wanted. Where all through the process, we have a lot of errors. Each errors indicates one type of information passes, and then it has weight. Weight is a process that we're training on. And overall, with more information input in, the weights will slowly adjust and then find the perfect or so-called perfect formula to get the results. A quick example down here, we can have a multi-classification problems. And from the beginning, we have a really simple line to draw this boundary. And when the process improves more, the boundaries starting to become more curvy, and the decision boundaries make it better predictions. And towards the end, it has a more curvy lines, and overall, you can see how the prediction can improve overall. While deep learning for typical data, such as gray-like data, 1D array, and 2D array are considered a little bit fixed size. First, for 1D array, we have text and speeches. And then we have 2D array for data frame, such as and images. And you can see how they always come in the fixed size, such as in this data frame, we can see like they all have a fixed features. And if we want to add more, and you only add more data in here. Example in here is such as we have input layers as an image, and then we have a convolutional layers. These layers will extract the pattern from this image. And then we have pooling layers, which is lower the dimensions and still improve the computation process. And then we have dense layers. These layers will transfer all the linear to non-linear results. And towards the end, then we have a prediction to say, oh, this image is a cat or not. So deep learning for grid-like data structure, which we call typical data, are considered a little bit different than graph data. In typical data, spatial locality doesn't need to take consider. So for anything in the first row and the second row, if we swap their locations, this neural network process will still give you the same results. While in graph, all the stuff are arbitrary size. If you swap one node to another, then the location where all changes, the graph will be a different graph. While in this data frame, the structure is simpler as well. While in graph, every nodes in this whole graph's location is really important. So you cannot change the nodes to a different location and consider still being the same graph. And this doesn't need any position informations, while nodes need the edges to build these position informations. And all the nodes edges, their distance are non-Euclidean, which means when the graph is in higher dimension, even though the edges look like in the same length, they are not typically are considered in the same length. So what do we need to do something special about graph data? First of all, we need to consider the topology, of course, because all the nodes information, the locations in the graph needs to be understood before we train these models. And as Victor mentioned before, nodes might have a different length of features. So the inconsistent number of features will be important to be used when we train this graph neural network. And also graph have edges, which means it has features, width, and directionality. And we all need to take consider instead of like typical data structures. Okay, now we have a simple understanding of graphs and deep learnings. Now let's learn it's a combination of both. Well, the same as neural network. Graph neural network, the main idea is gathering information with its nearest neighbors. Like, for example, like this. In this graph, let's consider this as a target. Then we want to build a graph neural network framework. The first, we can get some neighbors information from the first layers. So all these three nodes will become the first neighbors. And then we'll draw second layers for the second neighbors. So all these neighbors will be drawn like this. If we want to aggregate the information from its neighbor, then we come from the outside of the layers. So the nodes in this layer will then pass information to the previous layer. In the previous layer, then all the three nodes will then pass information to the target. And then when the target gets all the informations, then it updates itself with a new node embeddings. Another way to represent this graph is called computational graph. We draw it like up down like this. With this information drawn like this, so we have layer 2, and all the yellow nodes will pass information to the second layers, and then all the nodes in the first layer will pass into the layer 1, and then goes to the targets. Well, what happened in the black box, right? What does it mean to pass information and what the action does? The simple process can be summarized as like this. First, we can aggregate information from its neighbor to the current layer, which means it gathers information and have some aggregation functions and pass to the black box. And in this black box, we apply a neural network, which is called activation functions, and it will transfer this information from linear to nonlinear. And then towards the end, then we update the nodes embedding for the target node that you wanted. And this is a simple outline that we usually do. We have an input node embedding, and then we have k layers of GNN process. So this will one process, another process, and towards the end, we have our output nodes embeddings. Well, GNN have many type of architectures. When we call it GNN, graph neural network, it's actually a really general terminology that we apply neural network to graph. While there are three very popular architecture that we usually hear, I just want to give some simple explanation like what does it mean. First, we have a graph convolutional network. This is the most original graph neural network. This is just a process that I just explained in a minute. Basically, it just aggregate information from its neighbor and pass to the target nodes. Well, then we have graph search. Graph search grab sample nodes from its neighbors and build a trainable function. And in this cases, this function can be trained and put overload, so it can produce inductive prediction. Well, we don't know what inductive prediction yet, but I will explain in a little bit. And then we have graph attentional network. In this network, instead of focusing on all the nodes and all the features, this graph neural network has some mechanism can average the neighbor's importance, which means we can predefine what's important in certain nodes or certain features. For today's presentation, we're mostly focused on GCN because it's one of the, I would say, most popular ones. Okay, a quick explanation what is transductive and inductive, because this is kind of important in graph neural network. First, we have transductive. For transductive prediction, all the nodes has to be present before you train this neural network, which means if you want to predict a new node, then you have to put this node in the graph and train over or again. While this node doesn't necessarily need to have a feature or have a target labels, but it needs to present it before you train these models. Some example is just like original GCN. For inductive models, all nodes doesn't need to be present while we construct this graph. So just like in this picture right here, we can train in this graph while we can predict all nodes outside of it. While this architecture can be considered a little bit more complex, and all these nodes you predict in the new nodes must have really similar features as well. A good example is original graph set. So that's the main differences between these two. I know for today, since we are focused on GCN, so transductive prediction will be the one we're working on. And there are many types of GNN tags, right? For our graph, we have nodes. We want to know which nodes class each this node belongs to. And in this case, we can do node classification. And also, we can do link prediction. In this case, we want to know if this node might have a connection or what. And also, we can do graph classifications. Just move this a little bit. In graph classification, we want to identify how this graph behave in certain way, or is this graph some certain graph that we're interested in. Some simple example that how did we use GNN in real world. So there's 3 examples as what Victor showed before. First, we have a map. In map, we can use GNN to travel time prediction. Consider each node as a location and the edges is the road, the connection to it. And then for social network, we can do a label propagations, which means we can define and guess which nodes belongs to one class or another. And in here, we have graph analyze basically. So we can have multiple molecules and to see if these 2 molecules are more likely to interact with each other or not. So for today's example, we'll do a node classification. We'll test on if one person belongs to a tech nerd or not. Okay, so right now I have a basic understanding what graph neural network is and what it do. Let's say, how do we actually apply graph neural network to our toy datasets that we created? Before I dive into anything, I'm just gonna quickly do an introduction for the package we're using for graph neural network. It's called a PyTorch Torch Geometric, also short for PYG. Torch Geometric is built on top of PyTorch, so it has a really straightforward API, just like basic PyTorch. So in this well-maintained packages, you can build any comprehensive GNN models that we mentioned before, such as GCN, GraphSet, GAT, etc. And also, since it's really similar to PyTorch, so a lot of framework and flexibility still will be the same. So you can still modify a lot of stuff. Well, the basic framework is like this. First, we have input a graph, and then we build a GNN, and then we train and test these models, and then towards the end, we make the predictions. Just like a very typical neural network framework. Okay, now let's see the simple toy datasets. First, we have a node datasets. In this node datasets, we have some features. Right? We have this person's age, if he or she graduated from a master's degree or not, their salaries, hobbies, and the labels, if this person works in tech or not. And we have the edge dataset. For edge dataset, we have 2 columns. So if the 2 nodes exist in the same column on the same row, then we say it has a connections. While if we put it in a graph, it looks like this. So this is a graph presentation of these informations right here. And since in here, we all know the informations from each nodes, let's consider what if we don't know what a 5 belongs to in this class. So in this case, let's build a GNN model and to see how it actually works. First, just like all the neural network models, we have to transform all the string value to numeric values and you have to scale the continuous numerical variable to the same standards, because we don't want to have one columns that have higher range compared to other columns. Then you will dominate the for the decision boundaries process, I would say. And then let's start to construct the graph. For constructing a graph, we'll use this function called torch geometric.data. In this data, if you input the information in, it will automatically to transfer the information for you. Which it needs is all the information to be in the tensor formats. So in here, we have the node data set before. So we'll transform all the node feature to a tensor format, and we'll have the data label to tensor format as well as the edge. So you put this information in the graph object will be the graph that we're gonna start to work on. Okay, let's start to build a GNN model. Just like all the graph neural network model, you have to predefine some of the features or attributes that needed. For example, we need to predefine how many hidden layers you want, what's the activation functions, how many number of output classes, and of course, there are more information to define, such as optimizer, etc., etc. But in here, for simplicity, we'll just build a 2 layers neural network and use ReNode as active functions. Okay, since we build this model, then what happens in neural network? In here, let's just use node 3 as example. So for node 3, since we learned before that if we want to build neural network on top of this, we'll just gather information from its neighbor. So the first layers of neighbors will be 1, 2, 4, and the second layers will be extracted from all the informations in here, right? So in here, this process only showed for 3. Keep in mind, this whole things will happen to all the nodes that need to be trained on. So afterwards, then all the nodes will have a new informations and embeddings. Okay, so how many hidden layers do we actually need? For convolutional neural network, usually we want to more hidden layers if we want to solve a complex problems, because the more hidden layers you have, you can consider the curvy boundary become more curvy, right? So the decision can be made even better. Well, in graph neural network, this is not actually the case. Usually we will consider less to be better, because there's one issue that in graph structure might run into. It's called oversmoothing. Well, in oversmoothing, it's very similar like this. I'll show you in the animations I draw. The first, let's consider this to be our target, and we'll have first layers for neighbors and the second layers. While towards all the process, we can see how this embedding gather information from the whole graph. And now let's consider we need to build an embedding for these nodes. And we draw the first layers and the second layers. And you can see how these nodes get the information from the whole graph as well. So for a small graph or graph have a lot of connections in this case, all the nodes might end up being gather all the information from the same nodes, and they might have very similar embedding informations overall. In this case, when you train GNN, then all the nodes will just give you the same result. So in this case, we might not want to run into these issues for nodes gather all the informations or similar informations, right? So how many do we actually need? There are 2 possibilities. Let me just move. Theoretically, we want to calculate the diameter of the graph. So the diameter of a graph is the shortest length between 2 furthest nodes. So of course, you want the diameter be less than hidden layer has to be less than the diameter. But in practice, usually 2 or 3 hidden layers is more than enough. This is the information that we gather from a paper. So we have a classification problem with 3 classes, and then we have nodes from 1. We have hidden layer from 1 to 3. You can see how the accuracy improve when we leave up the hidden layers from 1 to 3. And towards 3, there's no actually major changes in the accuracy, right? Eventually, when you add more, such as like in here, you can see a downward on the accuracy. This is the issue we mentioned, like why sometimes when you have like more hidden layers, all the nodes will have the similar embeddings. So when you train your models, maybe you should start with 1 and slowly adding up to 3 to see which one give you better accuracy. Every data is different. Every data set is different. So you might want to test that on your side. Okay, After we build this GNN model, now we need to split the graph to do a test and train, right? But train and test split in graph is also different. Consider nodes to be independent. This is how we usually have it for typical data in grid-like data. So there are no connections between nodes or between the informations. If we simply draw a circle to select some train set and some test set, then this will have no issues, right? But in here, when the data points are dependent and they have edges connection between each other, we cannot simply draw a line like this. This will break the edges for the different nodes, and this graph structure will be damaged. In this case, one way to split this is called masking. For masking, instead of cut all the lines and select certain nodes, we'll simply put a mask on top of it. In this process, 5 will be considered dummy nodes, which means there's no feature information. It simply exists in here, but doesn't input any information we are training the models. In this ways, the GNN model will still know this node exists, but there's no information will be leaking. So that's how we split train and test. Okay, now let's train a GNN model. Well, train GNN model, the process is a little bit similar to how I explained it before. We basically have 3 steps. Let's still use 3 as an example. For different process, first, we will have the informations to aggregate it to the previous node. And then after this is aggregated, then we'll pass through activation functions. And when all the 2 layers of neighbors information already passed, then towards the end, we'll update this node, and this node will have a new embedded. Okay, let's just dive into a little bit mathematics to see what we're actually training in here. For in this, let's use node 3 as examples. First, we will have x3, x0, x1, x2, consider the informations it has inside, which is feature. So notice how in this node embedding process, the node itself will still need to take in account in the calculations. And then you can have some predefined constant to see the weights, to see the importance. And then what we trained on is this weights. So the weights will slowly changing overall while you do the GNN process, and you will adjust and to find a better calculation result for node 3 to belongs to in this class. Well, when we can write this formula in a more general terminology ways, so the nodes will start the training weights for itself importance information, and then you will train for all the neighbors, get all the neighbors information, and then train on these weights. Well, you can see the plus sign is in here, doesn't necessarily imply as a add. In here, the plus sign means the way to aggregate them. Well, this aggregation formulas can be defined as whatever way they want it. Maybe it's a mean, maybe it's max and minimum. So, but in here, we use the plus sign just as a presentation. Okay, after we did all the process and the model is trained, we know the weights, and this formula's weights is already calculated out. Then we want to make a prediction, right? Since we want a prediction on 5, and this GNN model is trained in 2 layers. So just as the same as before, for 5, we will get the information from its neighbor 0,4, and then it will expand to 0,4's neighbor, which is show up in here. After all this process is done, then the weights will, then the 5 will have a result of like which class it belongs to, and what's the possibility it belongs to one class and another. Okay, so this is a summary for GNN pipelines that we just learned. First, we need to impute a graph, right? This graph is created, and then we have a GNN model to get all the informations and pass by each other. And then we have updated embedding for all the nodes. And towards the end, since we want to predict 5, so 5 will be drawing neighbor information from its neighbor and make prediction for it belongs to one class or another. So do GNN helps in this case? Well, it actually depends. So in real life, there's many data sets right now stored in graph structure because some data just easier to be stored in that way, such as map and social network, etc., etc. In this case, we need some algorithm that can solve complex issues, which GNN in this case can be one of the best solutions. But also, where different data set might present a different result. So in this data set, we can see how when we only consider the nodes information as as a data frame, while we calculate confidence of 5 belongs to class 1. Logistic regression gave you about 56% that it belongs to class 1, while random forest gave you a percentage of 83%. While for GNN, while we're doing this calculation, we get 73%. So you can see how really it sometimes it really depends on the data set. In here, edges also provide information. So if you have some nodes with no features and only edges that provide a majority of the information, then GNN can be a really good way to solve these issues in here. Okay, so we understand how GNN applies to this really simple toy data set. Now we have a integration KNIME version of GNN. Let's see how we use a real life data sets and how does it represent it in, what kind of result it will give to us. First, a quick explanation for these data sets. This data set we gather is called a GitHub social network data set that we gathered from 2019. If you want this information of the data set, you can click the link in here, and we already post the slides information on the chat. So if you want to download it as well. This GitHub data set contains 37K of GitHub developer with more than 280 of connection collected. All these connections are between this 37K GitHub developer. So you can see there's a lot of information here. For edges represent the connections between two developers, and nodes are anonymized delivered information such as the locations, their job, the employer, right? And the target variable that we want to predict on is whether this GitHub user is a web or machine learning developer. Let's see what the data set looks like. First, we have an edge data set. Edge data set represents the connections. Well, it shows as the information or the toy data set I presented before. So if the two nodes shows in the same rows, means they have a connection, just as the example shows in here for the first row. So this node and this node has a connection. For node neighbor, we have the node's ID and the node's target. If the node is 0, means this person is not a machine learning developer. If it's 1, then it's another class, which means it is a machine learning developer. And then we have node features, well, which contains anonymized locate information such as location, employer, email, address, etc., etc. Where you can see how this nodes looks a little, or how this data set looks a little bit different than what we had before. This is all numbers and it's all in a weird format. Well, the issue we run into here, right? First, we can see how the nodes might have different features. So some nodes might have the numbers that other nodes doesn't even have at all. And also some nodes might have some more features compared to other nodes. Well, this doesn't really exist in a grid like data structure, right? Because all the nodes will have the same length. In this JSON file, all the nodes are arbitrary size. So you cannot assume the nodes, the information exists in one node will be the same as other nodes. So to solve this information, this problem, so we can transfer all this data set of JSON to a sparse matrix. With sparse matrix, with really big sparse matrix, we'll maintain all the informations from different nodes. If this node has these features, then we'll put 1 in the sparse matrix. With this sparse matrix created and edge node information ready, and this is the workflow that we build it that it can use to build GNN workflows. And this is the GitHub link in here if you want to download and test out yourself. The process is really simple, as shown like this. This is really typical KNIME workflows for building any machine learning process where we have a learner and a predictor. And of course, you need some information to put it in, and I will explain one node by node. Just some quick requirements that we need for this node to build it, since there are many different ways to present the information for nodes and edges, such as sometimes in when the edge data set you get will look like this. You might have one column, just as one number, and another column, it's a list of number, which means there are a list of nodes that is connection to these nodes. In this case, you have to transfer into this format. So which means 2 numbers exist in one row, which means they have a connections. And for nodes data set, it has to be standardized and all the node with all the node features. And you need a target variable with target columns, Otherwise, there's nothing to be learned or trained on. And then you need a unique node ID, which means it can represent the connections between here as well, right? And so you need to have an index number, and you need a target variable, and all this standardized numerical value needs to be standardized. Yeah, so that's the requirements. Okay, now let's see the constructed graph parts. So since we mentioned the nodes data set, it's not exactly what we wanted. So this is the process we transfer information to sparse matrix and gather some information here and there. And then towards the end, we have the data set that is exactly match our requirements. For edge data set, since it's just the same format, so there's nothing we need to do about it. Okay. So when we want to build a graph, we have the edge informations and we have the node information. We just put these two informations to the GNN graph creator nodes we created. In these nodes, you need to select the key, which is the node index, and you select the machine learning target columns, whatever your column name is, and you need the two edge columns to indicate these two nodes has a connections. While those created, these nodes will build graph objects. Okay, with the graph object created, now let's try to build a GNN model and train on it. First, we need a partition in nodes, right? Because we want to do a train and test split. While we said before, graph neural network or anything with graph structure cannot be simply split like this. What we did in here is all the hidden, all the masking or hidden process, it's hidden in the learner and predictor process. In this way, the partition node doesn't really necessary to be the only way to split your nodes. You can use other nodes to split your data. It just on the top part, you indicate what kind of nodes you want to be trained on. And in the lower part, you can indicate what kind of nodes you want to be tested on. While in here, we just use a really simple partitioning nodes to split data sets into 70 and 30%. So the first 70% of nodes will be used for training, and the 30% of nodes will use for predictions. And then since the nodes already, since the GNN learners knows the graph nodes and knows what part of the nodes you want to be trained on, GNN learners then will train on those nodes and get a trained models. And yeah, since mask is included. And what you need to select in here is you need to select how many hidden channels you want and how many hidden layers of this graph neural network you want. Of course, for all the neural network, we need to define the learning rates and how many epochs, which is how many times you want to train on this GNN model. And this nodes will output a trained model. After model is trained, now we just need to pass this trained model to a predictor. Well, this predictor will get information from the trained model, and then you will get information from the partitioner nodes what part of nodes they want to be tested on. With all this testing, and then towards the end, you will give your prediction for different nodes that you want to have a result on. This is the output of these predictions. So first we have the key for all the nodes. So all the nodes is they will want to be tested on, pretending we don't know what class this belongs to. And this is the true value, which is the target variable of like if this person belongs to 0 or 1. And this is the prediction of this nodes give the results. Okay, so we have one new data frame with true value and predictions. Now we want to do some evaluations to see what the result gives us, right? Okay, for evaluations, you have to have true values of your test nodes to be valid on, right? If there's no true values, then you don't really know like if this node is predicted correctly or not. But since we have the information in this dataset, so we can do it. And also we use the Scholar nodes. This node is specifically for classification problem. If you have a numerical issues or numerical datasets, then you might want to use called numerical scholars. It's a different nodes, but really similar, looks like this. So in this nodes, you select your target variable, your true target columns, and then you select the predictions that you made. With epoch 20, so we trained this model 20 times with a learning rate of 0.1. It gave us a confusion matrix like this. and the accuracy is 86%, which is a lot better than 70% of our baseline with only epoch 20. So you can see with such a big data set with a lot of information in here, with only really simple GNN models, it can still give you a really good result. And all those training time, I think it's less than 1 minute. So I think it's really powerful. Okay, some advantage and disadvantage and the limitation of GNN. Of course, since it's called a graph neural network, it can handle graph, which is the data of very complex data structure with topologies and complex information between nodes and edges. So this is one of the advantage. Also, you only get the information from its neighbor. So expanding through its neighbors, we can see how you use information and data really efficiently. The limitation, like I mentioned a little bit before, it's how it might really varies depends on the data sets you have, right? Sometimes some simpler models might even perform better than GNN. So you might want to test out to see if your data set is suitable. And it might have scalability issues, of course, because the GNNs in different sizes, and we sometimes it's absolute sizes, and sometimes you want to add more new nodes on it. Well, in these papers, we gather some information you see in this, in the notes in the data set we tested before. We can see how logistic regression did not outperform in graph search. In this case, actually, it got beaten by a lot. So yeah, so different data sets, different results. So just double check with yours. Okay, so since we know how cool this KNIME can do this with other GNN building, now Victor gonna show you how to do this integration with Python in KNIME.
Thank you. Okay, so next we're going to end with building Python-based tools for graph neural network in KNIME, which is a more precise look at Python integrations within KNIME. So for instance, let's compare a KNIME versus a Python solution. So a native KNIME solution, for instance, to draw a graph might be first creating the network with our object inserter node, and then viewing the network with the network viewer node. And you would get this kind of visualization. But let's say you have been working for a long time on a Python solution using the network X library, right? And you perhaps like this style a little bit better. So you want to continue using that. So how then do you use Python in KNIME? So there are two primary methods. I'm going to talk about the first one, which are KNIME native Python nodes. So we have nodes such as Python script, Python view, and this allows a simple Python script, which you can actually put directly into KNIME in the platform itself. So you see here, I simply add a few things which translate the KNIME table into a Python data frame. And then from there, I simply output it back from a data frame to a KNIME table, and I'm able to view that. Now, another way, instead of directly writing in KNIME, is to use our Python extension. And this allows you to have complex Python scripts that are outside of KNIME. So you can see here, I can write within Visual Studio Code, and then I can bring that into for instance, a GNN learner or a GNN predictor, however I like, and with images that I like. It makes it look a little bit more professional, and it's much easier to collaborate when you use this style. So let's talk a little bit about this more complex style, the Python extension node. So there are 3 steps for creating this type of node. You need first to have KNIME Analytics Platform on your computer, and you need a basic folder, which we will show you how to download a little bit later. You will also need to establish a connection between the KNIME Analytics Platform and this basic folder. Finally, you will write using the Python KNIME API, which I will also demonstrate. So I'm just going to list this here, but of course you can download the slides. The link is in the Zoom chat. For those of you who are here, I can share that with you as well. But basically you will need KNIME, you will download the extensions, and then run a few things to get the basic folder up and working. In the basic folder, you will have access to several different files that you will need to configure, such as this config.yml file, the knime.yml file, and of course the myextension.py file, which is where your code will live. You will then establish a connection. Again, I'm just going to leave this here. This is mostly for your reference at your own leisure. But basically, you'll need to change two files, the knime.ini file and the config.ymi file. Now, if it worked, what you'll do is open up the KNIME Analytics platform and you should see your node. This will just be a test node that doesn't have functionality until you start to populate the code. So of course, we're going to write some code. The coding itself, we're going to use a class, and above the class, we put decorators. And these decorators will literally decorate your node. So they allow you to, for instance, choose a name for the node, how it looks in the KNIME Analytics platform, what kind of inputs, what kind of outputs that you want. And this all comes before the class. Within the class, you can then instantiate some parameters. And this is what Jinwei was showing you earlier. So when you double click on a node, you can then say, I want 16 hidden channels or 10 or however many. Looking at, you can change the learning rate, you can change epochs. And this is for the user. Now for you, you will actually be dealing with two primary functions, which are going to be configure, and execute. In configure, it's really about specifications and rules. So telling KNIME, okay, invalidate or raise an error if the person doesn't give me a string as a type for one of the columns that they've given. And execute will actually be what you're going to do. So I'm going to train this graph neural network. I'm going to load it as a pickle from a pickled file, et cetera, et cetera. Now, the difference between the KNIME native Python nodes versus these created extension nodes is that, for me anyways, the native Python nodes are easier to use and they really help with rapid prototyping, whereas the created Python nodes are far more powerful and they give you more control, modularity, versioning, right? I can work with someone on GitHub and I can collaborate with them in order to get what I really need working and in my, for instance, corporation. Now, there are lots of resources additionally that you can use to check out how you build different types of nodes. So in this presentation, we talked about building a learner and predictor motif, which is to say a basic machine learning. But if you want a different kind of Python library, you can also use that as well. So in this talk, we talked about graphs, deep learning, and graph neural networks, and we showed you how we applied them on a toy dataset and also on a benchmark dataset. Finally, we taught you how to build Python nodes. And of course, you can use these resources all to build your own nodes or to build off of the work that we have shown you, because this is open source and free software. So future work, for instance, if you were interested, might be working on light GCN or simple GCN or PinSage, which are more scalable graph neural networks. There's also edge prediction and graph prediction, because all we've shown you today is node prediction. And of course, things like bias and explainability, fraud detection with, for instance, an interesting loss metric by Facebook. And we have gathered many different sites together and put them here so that you can go ahead and check out some different things for graph data sets. And if you're interested in KNIME, we have Q&A websites, we have workflow repos where you can download other people's work. And of course, we have YouTube videos that you can go ahead and watch in case you're wondering how do you do certain things like this video, for instance. Thank you so much. We'll now take questions from both the online presence and the in-person people. Okay, are there, yeah, there's a question in Zoom. Okay, can you read it to me?
Yeah, so how would you use the trained model to make a prediction on nodes that is not part of trained as data
Yeah.
sets? That's the question.
Yeah. So let's go back to looking at Jinwei's example on that. But basically, there are two primary ways to do this, depending on the architecture that you're using. So if you're using a GCN, for instance, then you're going to be, did I go fast? Yeah, perfect. Okay. So there are two primary ways to do this. When you're using a graph convolutional network, for instance, you will need to put that node back into your graph or into the graph to begin with. And then you will need to retrain your model. And you don't have to have this node labeled, of course. You can have it with no label. And the graph neural network can predict on it. Now, if you want to go ahead and take our work and do something more powerful, more complex, you can try the Graph Sage architecture. And with the Graph Sage architecture, what it does is break the graph into pieces, and then it learns about the graph on a more abstract level. And then it's able to, for instance, predict on several nodes that come in, as so long as they share the same features. So there are two different ways to do this. One that we showed today was the transductive version, which requires everything to be present. Even the new nodes need to be present to predict on them. Or the inductive, which is taking a group and predicting on them. But this architecture is a bit more complex. Live audience, any questions? No? Okay.
So there's a question, Alexander. Is there a differences in deleting a graph node or deleting from the graph? I think they're both the same thing. I'm not quite sure.
Yeah, you want to try answering that? Let me look at the question. Go ahead.
I'm not really sure like what you mean to deleting a graph nodes or deleting from graph. I think if you delete this informations or this row before you considering this graph, then all the edges information might be lost, and you have to delete all the edges connection from the edge dataset as well. Yeah, if you just delete it from the graph, construct the graph itself, then all the edges information will be disconnected, just like that. Yeah. So they're more entirely, I mean, mostly it's the same thing, I would say.
Okay. And then there was another question about whether it's possible to make Python-based node by using a Python environment instead of a Conda environment. So I'm not 100% sure on that one. I would have to ask our developers if it's possible to use a Python environment. So I will post this question to the KNIME forum, where we have this, and then I will get back to you, Alexander. Thank you. And the first deleting means masking. Sorry about that. Okay, so then his question is there a difference in masking a graph node or deleting it from the graph?
Oh, yeah, it's actually quite different. Let me put the slides where to about masking. Yeah, so in here, the masking process is one way you want to split the data set. What it does in here, and put this masking in here, what it does is this 5, it still exists. It's just like when we train it, we pretend the 5 to be a dummy nodes. Dummy nodes means that this node only exists in here, but it doesn't have any features information. It doesn't leak any true label information. It's just in here. And then when we test it, when we test it, then all the feature information will be still in there, and it get information from its neighbor, then it will have a true value. While if you deleting these nodes, such as like in here, right? If you completely cut it through, then these edges will lose connections as well. Then this gonna be a completely different graph than what we consider.
Yeah, I agree. Yeah. Okay. So those are all of the questions, I think.
Okay.
From the Zoom audience. So we will maybe wait 2 more minutes. Yeah. And then we'll close the Zoom session so that we can do the live in-person networking. Do you have any questions from the in-person audience? Okay. Okay, so we'll give it 1 or 2 more minutes, and then we will close the Zoom session. Thank you, everybody, for coming today. Yeah, I think we're okay. So thank you, everybody, for joining us today. We're going to be closing this session off. Yeah.
Thanks everybody for coming.